You might have to. So you might have to turn down and mute it. And control this down.
Oh, it's still coming in. Yeah, that should mute it.
Correct, sir.
That's weird.
There must be, oh yeah, because that's so yeah, but I don't know why that's still putting us
Oh no, I'm good, thanks, man.
Some guy that told me everybody else, you know, it's kind of stuff. We started yeah, I hope I'm glad it holds up.
Yeah, that was
6, 7 more months of that.
Well, I guess we should get started. Thanks for coming, everybody. My name is Ed Peterson. I'm with Northwest Motor Service out of Longview, Washington. Also with us is Spencer Wiggins of Northwest Motors. He's the owner. And Dave Wollinger, Northwest Motors, is our field service manager. So appreciate your time today. What we're going to cover is I'm going to start off with some motor basics, and then a little bit more involved in motors, and then Dave's going to end it up with a little bit of safety and motor testing presentation as well. So my background is I started in the motor business in 1984 with GE and down in San Francisco, and kind of worked from San Francisco to Seattle, moved here in '88 and moved to GE up here. Also was with North Coast for a little while. So sold some Reliance drives, Allen Bradley drives, GE drives, GE motors, Reliance motors, pretty much everybody's motors over the years. And so we're just going to talk a little bit about some of the technical considerations of motors, how they work, and what you can do to extend their life for your customers. So that's a little bit of the topic. So these are the two basic components of a motor. So you've got the stator and the winding, or the rotor. Inside the stator is electromagnets, which we're going to talk a little bit about how that's done in here. And then the rotor bars are the corresponding element in the motor that works with the windings over here to induce magnetic torque into the rotor.
You want to get this thing, see if we can write this thing down. Sorry. Echo. Yeah, it's echoing back through. Yeah. Getting worse.
You might have an idea on how to mute this thing, Evan.
Is it okay?
You like it? The down the board right in front of me.
There's the speakers on right here. I don't know how to turn the speaker on this.
Hey, you'll be late again. I would eat more than just 2 almonds and that. Yeah, more than just dry tuna. His body just don't come back. Close the door out.
I got it. So the components inside the motor. Should I stand over here? No. Your sign language.
You guys put some LSD in this food or what?
I don't know what to do with this.
You just turn down that speaker?
Just turn it down.
Well, that one's muted.
Did you say goodbye to the guys that are Skyping?
I don't want to say goodbye to the guys who are Skyping. I'm not sure where it's picking up the sound. Does that come through over there?
I have the volume all the way down. There's no way.
Okay, try that. All right, so components inside the motor are the stator windings, the stator, the rotor, of course. This is the outside enclosure, the air gap between the rotor and the stator, and of course the motor shaft. So if we were to look at the corresponding poles, there's 2 poles, positive and a negative for every one of these. So they're 180 degrees opposed, okay? And we're going to show you how that works. It's basically just the old, like a magnet on a string, north and south attract, north and north repel. So that's basically what's happening inside that motor, is that we're switching the between the 2 poles. So half the time the motor is pulling towards the next pole, pushing away from the last one. So that's how we're getting rotation in the motor. This basically says whenever you have a piece of steel between, or iron between 2 magnets, it's cut those lines of flux, which is showing here, and then you've got magnetism induced into the rotor, is all that's shown there. So again, this is the positive and the negative, the 2 poles in pairs. So this is basically what's happening in one cycle of a 60 cycle machine, right? So we start off in the first position. We've got the first pole here at all these on north, positive and negative, shaft position there. And then it just starts to go around to the next pole. So it's being attracted to the north and pushed away from the south. And that just keeps continuing through every phase of that cycle, producing shaft rotation. So this is the formula behind that. You can tell the RPM of your motor if you take 120 times the frequency that you're running at, which normally is 60 hertz unless you're on a drive or something, divided by the number of poles. So we commonly in the motor world talk about motors as 2, 4, 6, 8 pole machines, 2 pole machines of 3,600, 4 poles at 1,800, 6 poles at 1,200. And back on that previous drawing, well, too far to go back. You can see that last one had 3 groups of negative and south poles, right? So that's the pole group that we're counting here. So if you divided all that out, so this 120 times 60 is 7,200. So the basic formula is 7,200 divided by the number of poles equals your RPM. So this is a 4 pole, 7,200 divided by 4 equals 1,800. So if you didn't know the poles on your motor, but you knew the RPM and you wanted to know how many poles are in it, you could back into it that way. Or if you knew the poles but didn't know the RPM, you could also back into it that way. So this is just a little chart basically showing what we were just talking about, the 2-pole, 4-pole, 6-pole, and 900 RPM. Now there's a difference between synchronous RPM. These are all synchronous speeds. The motors don't actually run at that speed. They run slightly slower than that due to a phenomenon called slip. And slip is the torque producing component of the motor winding, so it's really important. We're going to get into that in a minute. This is another useful formula. If you want to know what your horsepower is, you can take, well, torque is usually an unknown, so it's usually you're working this way. If you're wanting to solve for torque, take the horsepower times 5250 divided by the RPM, and that equals torque. There's a simple little, I guess, shortcut. If you're using an 1800 RPM motor, the horsepower times 3 is your torque. So if it's a 5 horsepower motor times 3, it produces 15 foot-pounds of torque. So for a 4-pole motor, it's 3 times the horsepower is your torque. There's just a couple of little applications of motors in your world, and I'm sure you guys see every day. These are all, pretty common. We don't do this kind of blower motor. We should. That looks like a lot more fun. One of the things that I wanted to kind of talk about today is, I guess, the type of motor your clients use. We're from Longview, down in the industrial market down there. We've got like 5 pulp and paper mills in town, just a ton of industry. And everybody in industry, I gave you all a brochure, I'll borrow yours here. It's this one right here, this Genie 841 brochure. In the industrial world, pulp and paper, petrochem, that sort of heavy industry, this is the type of motor everybody uses. The specification is called IEEE 841, and that's a standard that all manufacturers adhere to certain benchmarks in that design. So you get a 5-year warranty in the 841 motor. You get very low balance, which makes your bearings last longer. Keeps vibration out of the system. So there's a lot of driven equipment advantages to having low motor bearing vibration. They run really cool, so you can put them on VFDs without derating. They're just they're what we stock because it's what all our guys use. Now I know in the HVAC world, weight is an issue, and sometimes the lighter the motor, the more it's the more it's liked, just because it's easier to put it up on the roof or wherever you're trying to install that motor. From my point of view, a heavier motor is better, just because you've got more mass there. It helps with vibration. It helps in heat dissipation. There's a lot of advantages to a beefier, heavier motor. There are disadvantages when you're carrying that up a ladder or up a bunch of flights of stairs, and I get that. But one of the things I wanted to show you guys, this type of motor, which I kind of doubt most of your customers use because it's a little more expensive than the cheapest motor you can buy. And a lot of times guys are just concerned about first cost, and they want to get back up and running again, and they want to put the cheapest, most available motor in there. If you look at payback cost of a higher efficiency motor versus a standard efficiency motor, it's usually kind of a poor decision to go with the cheapest, lowest cost, because motors don't cost that much. I mean, you might spend a couple of grand on a 100 horsepower motor. Well, that motor consumes about $75,000 of energy in its first year of operation. So if that $2 grand motor, and you're talking the delta between the best motor you can buy and the cheapest is maybe a couple $100 or 10%, so you're talking 200 versus 2,200. But you're going to spend 75 grand running that motor in the first year. My motor is only going to cost 68 grand to run in that first year. There's a real easy payback. But you got to find the right guy who's willing to understand that and have that conversation. Because a lot of guys don't care about payback. That's not their department. They don't work in that department, right? They don't really care. But there are a lot of advantages cost-wise. Overall life cycle cost of this motor is lower than the cheapest motors. And the performance is higher than any of them. They run cooler, they run at better efficiency, and they run longer. So you'll have less downtime over the life of the motor. So GE breaks down their classification of motors in kind of a good, better, best. The first one is the Energy Saver. Next is the XSD Ultra and the XSD Ultra 841. XSD stands for Extra Severe Duty, and that's the one I just showed you on the flyer, this third one down here. The Energy Saver is a cast iron product. It's high efficiency. It doesn't have the 5-year warranty. It's what we have to do to kind of compete with the Lincolns of the world, some of the lower cost guys that are out there. it's still, in my opinion, a better motor than those. And we're going to get into some construction features in a little bit that I think supports that. For a little extra money, there's the Ultra, and for a little bit more money, there's the 841. I think where you're competing, I doubt your competitors are trying to move that high of a quality of motor. So I don't know if you have an opportunity to talk value with the customer, but if you do, it's a pretty easy decision to spend a little bit extra to get the best you can get. That's going to last, several times longer. They also make a couple other featured motors. This is ASD, which stands for Adjustable Speed Drive, and that one's optimized for VFDs. Now, when I say optimized, this 841 motor works on a VFD. When I say optimized, on the back of that brochure, there's a picture of that type of motor. I lied. I'm sorry, there isn't. They'll have a blower on them because in everything with the motor, well, all things electrically, really, heat is the enemy. So anytime we're able to have a motor run cooler than it's designed to run, we really extend the life of the motor windings and the bearings, the grease in the bearings, and they just last a lot longer. The problem is on a true VFD rated motor, where we say there it's optimized, that's when guys are going to run really, really slow. So these are totally enclosed fan-cooled motors. So on the back of the motor, there's a fan that's shaft-driven, right? So if you were to put that motor on a drive and slow it down to maybe 200 RPM, and it was designed to run at 1800 RPM, you're just not getting the airflow over the motor anymore because that fan's not turning as fast as it was designed to turn. So your motor's going to get hotter because it can't dissipate the heat as it was supposed to with that fan. So what they do on these that are optimized, they have an external blower motor that always runs at 1800 RPM, independent from the main motor, blowing constant velocity air over the motor. So it cools, and they can run at like 0 speed, really slow speeds. And I'm not kidding, literally 0 speed, full torque at 0 speed. You probably don't have any applications like that, but they're just, they're commonly used in industrial plants where you have to have, like on a paper machine, where you're going to run really slow and you have to really regulate torque and that sort of thing. The Quantum line is bigger stuff. That's like 300 to 800 horsepower. And those are fully featured. They have space heaters, RTDs in the windings and bearings, so you can tell how hot your motor is getting in the windings and the bearings. Just full features and high efficiency. Then also verticals, large AC. Those are thousands of horsepower, and then DC. So GE makes a pretty full line of motors. What they don't make, the conspicuous hole in their product offering, is the small stuff, the 4856 frame, fractional horsepower, half to 1 horse. That kind of small stuff, single phase and 3-phase, they don't make. They sold that off a few years ago, so they got out of that division. So I don't know if you guys do a lot of motors under 1 horse. If you do, GE isn't really much of an option. But in the integral, 143T and up, they're a really strong player and they have a pretty solid wide line. So some of the strengths of GE is, they're known in the industry. They pretty much developed the electric motor along with Westinghouse back 100 years ago. So they have a ton of technical expertise. They've pretty much seen every application over the last 100 years. They really excel at making custom motors. So if a customer has a double shaft motor, or if they're asking it to do something unusual from its torque requirements, maybe it's starting up a really high WK squared inertia blower, that's the kind of stuff that they excel at. They'll do all those calculations. Of course, they're because they've been in the business so long, they have a huge installed base, particularly here in the Northwest. On our 841 pricing, so as I was talking about the good, better, best, we actually, because we sell so many of these 841s, we were GE's largest or fastest growing distributor in 2015 in the world, which is amazing to me out of Longview, Washington, that we could have done that much business. The result of that is we get the best pricing in North America on that product line. We can actually price this motor about where other guys are selling their middle of the road motor, not their lowest grade, but their middle of the road motor. So we can sell the best motor, in my opinion, that you can buy for about the price of what everybody else kind of medium grade is. So we have real cost advantage position on the competition. When you look at other competitors, 841 to our 841, there's a big delta in price. And I think if it's something that you guys wanted to pursue, I think it'd be a pretty good profit opportunity for you to upsell a customer into an 841 and get a premium for that. We stock those in Longview from 1 to 300 And then we've got some of the medium voltage, the quantums up to about 600, so go a little bit larger in those sizes. Medium voltage is 2300, 4160. I don't know, you probably do get into motors that size occasionally, but most of your stuff 460 probably that you do?
Yeah.
300 and down, that kind of
460.
range? Yeah. So that's a picture of the 841, and I brought a little cutaway of it here because I think it really helps when you can see inside the motor some of the features. I saw you had a little Westinghouse motor over here, and that's an older motor from the 80s, and it wouldn't really be fair to tear it apart and compare the two because they're just completely different animals. This is an industrial, heavy duty, and that's, just a kind of a cheap, plain vanilla motor. But if we took them apart, you can really see some of the differences, and I'm going to go through some of those now. So that's what it looks like from the outside. On the inside, there's a couple of features that really make this motor so rugged, and it's the reason it lasts so long in industry. The first thing is, this is an oversized bearing on the drive-in, and so it's one size larger than NEMA requires. And on the back end, they put the same size bearing here that they put here. That's uncommon. Most guys put a smaller bearing back here, because this one carries all the load, particularly in a belt drive, right? So this is going to get all the radial load. But in reality, what happens is you've got a small bearing here, and you've got a belt and a pulley out here. This is your fulcrum. The lever action starts to wear on this bearing too. So when if you compromise your design and put a small bearing on there, you've just moved the point of failure from here to there is all you've done. So Genie gets around that by putting an oversized bearing front and back. So they're both oversized. L10 life, which is the number in which 10% of the bearings will fail, is 130,000 hours, which is around 13 years. So only 10% would have failed in that time. So it's a super bearing design. One of the other things is the limit, that IEEE 841 specification has a limit on the vibration at 0.04 inches peak to peak. These are at 0.02 or less, every one of them. So they're half the allowable vibration. So that just has all kinds of benefits for vibration in driven equipment. It helps the bearings last longer, of course. There's some other neat features here. This I know you can't really see here. This is, so there's 3 phases here, A, B, and C. And they're separated here with probably Mylar or Nomex.
Yeah.
And the other thing is the bracing. All these interns are tied. So you can kind of tell when you open a motor and just look at a cross section of it, the frequency and the increments of that bracing kind of tells you a lot about how well that motor was made. Inexpensive motors, you might see bracing every several inches, and that basically. If you think about what's happening every time you start a motor, right, the shaft wants to go one way. Well, Newton's law tells us if the shaft wants to go this way, these windings want to go the other way, right? The only thing that's keeping that from happening is the fit between this, the stator core and the frame and the bracing on these interns. Because every time you want to start that, it's particularly susceptible. This is called the crown of the motor. This is the stack, where these are all laminations of steel. These windings go all the way through here. At the interns, this part that sticks out is called the crown. Now, the part of the winding that's inside the slot here is pretty well, held in place by the slot that it lives in. It doesn't get to move around a whole lot. But out here on the end, you see a lot of flex. And we've got actually a slide that shows that in slow motion, how much flex is happening there. The downside to that is, as these flex over time, every one of these wires is insulated, and if you get that movement, you get some abrasion on those, and you can wear away your insulation on every strand of those wires is insulated, and if those insulations wear, then you've got a short. So that's the beginning of the end, as they say. So the bracing is another great feature on this. This is all of these motors come fully greased. There's a big grease reservoir here. This is a cast iron bearing cap. GE's the only one that does that, and they use them on the front and the back. So that's these right here, and that just clamps the motor in, and they're gasketed. So in the event that somebody's re-greasing this motor and hasn't undone the grease relief on the bottom so the old grease can purge, which does happen, normally under that condition, you would just be pumping grease inside the motor when your purge is blocked or haven't removed the fitting. With that gasket there, that makes the path of least resistance back out the shaft. So extra grease purges out along the shaft rather than back into the motor. Because when you get grease inside the motor, then it gets hot, it carbonizes, and it becomes a conductor. So that's motor failure as well.
Those
So-
normally have open bearings on them.
So these
They're
are
greasable.
These are regreasable. They're open on the outboard side and shielded on the inboard side. So again, to facilitate that grease path, but not get grease back into the motor. What am I leaving out, Dave? Anything else? Impro seals, front and back. Impro seals are designed to keep contaminants out of motors. You see it here. You can hit these with a 90 psi pressure gun. Won't get water inside the bearing. They're not washdown motors. They do make washdown rated motors that are designed to be, hosed down continually. They'll run submerged practically for a little while. These are mostly just designed to keep out moisture and contaminants and stuff out of the bearings. And then the lifting lugs, this is kind of a neat feature. That one doesn't have one. A lot of them have eye bolts, right, that just have a screwed in eye bolt here at the top. That's really pretty dangerous because when those threads back out, a lot of times when it's even on the hook, the motor rotates, comes off the thread, crashes to the floor, hurts somebody, damages the motor. These have 4 cast-in lifting lugs. Each one will support 4 times the weight of the motor. So you could, your motor and your driven equipment could come with it. You can pull your pump and your motor not disconnected as long as it's, within those weight limits of 4 to 1. So you've got one here. You would have one here. It's been removed. And then there's also on the bottom of the motor here and here. So if the motor's mounted vertically, you can still get your hook into those holes.
What on that cutaway shows that it's rated vertically?
So let's talk a little bit about vertical applications because there are some considerations we have to make. For GE at about 75 horsepower, that's when the weight of the rotor starts to become excessive for what the bearings can handle. So if your belt drive, shaft or shaft down, up or down, doesn't really matter. All the weight of that rotor is hanging, on those bearings, right? So it's just not ideal. For GE, that number is about 75 horsepower. Above that, what they like to do in shaft up or down applications is they actually redo the grease path so that we're not feeding grease in from this side. We're feeding grease in from this side. Say it's shaft down. So this is going to be the down side. We want the path to come in from the high side of the bearing, purge out through the low side. So we basically flip these seals around. We also either pin or throw a weld bead around the rotor to the shaft so that the rotor doesn't slide on the shaft. Those are basically the 3 things. You got to repath the grease, pin the rotor to the shaft, and just let us know. If you're applying these over 75 horsepower, we will have to make those modifications.
There's nothing under 75?
Yeah, under 75 we're good. That may vary between manufacturer to manufacturer, but I'd say that's probably a good rule of thumb for anybody's motor. Above 75, I'd start to worry a little bit, just because it's a lot of weight to hang on those. They're really not designed for that much axial play. It's more of a radial load they're designed to take and just overloads the bearing a little bit.
And I guess one other note there, or thought, is 75 horsepower is also where we start seeing manufacturers introduce roller bearings for belted applications.
Right.
So that kind of becomes that tipping point where you go, I can take any NEMA motor off the shelf and it's probably going to be okay. 75 horsepower, there's more application consideration. So we're going to be asking more questions. Anybody's going to be asking more questions specific to that application. And that's again pretty standard. NEMA standardizes a lot with electric motors from manufacturer to manufacturer. What they don't do is say, here's where you need a roller bearing versus a ball bearing, or where you can go vertically or not. But we see those changes happening at about 75 horsepower for most of them.
So let's talk a little bit about motor failure. Most motors fail due to mechanical reasons, not electrical. And it's usually the bearings or something associated with the bearings. They either got dirty, contaminated, they weren't re-greased, they were over-greased. Over-greasing really causes more motors to fail than under-greasing if you look at the stats on mortality on motors. There's a lot of different philosophies in the industry about maintenance schedules on motors. Should you re-grease a motor? Should you not re-grease? Should you just let it run to failure? There's a lot of people that have actually decided that their motors run longer if they never let their maintenance guys lube them. They just run to failure. I wouldn't recommend that on an expensive motor, on a really large expensive motor, but on something of this size, that's totally understandable. That motor will run at least 7 years without ever being greased. Now, I hate saying that. That's
music to
don't ever repeat that in front of a GE attorney. I didn't say that, but that's if it's normal duty, not super hot, not super contaminated, but just a normal application, 7 years, all day long.
Their Energy Saver motor now, so their entry-level motor doesn't even have Zerk, so it's not a greasable bearing up through, I think, a 280 or a 320 frame. So it's pretty good sized motor before it even becomes greasable bearings. So.
Well, it seems like half the time or more that you open up a motor and the bearings are sealed anyways.
Sure.
And it's got Zerks.
They don't have a Zerk in the grease seal bearing.
Right.
You know, the reality is if you've got a 100-horse motor that's lost its bearings, and that's the only thing wrong with it, it's just bearings, you're still kind of looking at it's cheaper to get a new motor than even just do the bearings, you know, even at 100 horse. So there's, you know, it's a fine line. I mean, and it's kind of, the building owner probably makes that decision. I don't know if
We do a lot of them from 5 horse and above
yeah,
because it's just quick and easy.
to do the bearings.
Yeah,
Do you?
they're cheap and
Mhm.
they're easy enough.
You do them in house.
Yeah, we'll just
Yeah.
do them in the field.
Mhm. So these are just a couple. I love this one. Talk about overhung load. So I know you guys, I assume most of your applications are belt drive, right? I mean, some coupled, right? But probably all, mostly belt drive. So you see a ton of this, lots of shivs, lots of grooves, too much, overhung load. That's just amazing to me. The picture almost doesn't do it justice from the scale of this, but this shiv is about as long as that motor. The shaft is way back here. It's just insane, you know. When I saw that, I have to take a picture of that one. So this is a grease compatibility chart. This is another big thing. Now, do you guys normally re-grease motors? Is that part of your maintenance contract with your clients?
Kind of got their own kind of schedule.
Okay.
I mean, we try to spec out using Polyrex EM
Yeah.
for motor bearings and a different type for pellet blocks and stuff. But I mean, and then customers, of course, there's customers that spec out their own grease or have certain requirements. But
So the main thing on
all
greasing,
aboard.
and I'm sure you guys are probably aware since you do re-grease, is, you know, these are all Polyrex EM grease. The main thing is to watch out for lithium and that incompatibility. That's the most common gotcha that we see is guys mixing lithium with polyurea. They don't work. So I hope your clients tell you what, you know, if they've gone to something other than polyurea, that they've told you that, and your guys aren't putting poly in a lithium, you know, motor. That would be terrible. So hopefully they're sharing that with you, or you get to drive that decision.
Or nobody knows.
Yeah, they'll find out eventually if there was any incompatibility. So there's a bunch of different types of greases. Of course, the most common is polyurea. So this chart just shows what works with what. And I know it's hard to read. If you guys want copies of this, I can give you copies. And this is a relubrication schedule. Again, I know it's a little difficult to read. But basically, I'll just pick one here. For standard duty, 100 horse, horizontal, every year and a half if it's horizontal, 6 months if it's vertical. So a lot of guys, you know, their regreasing schedule, maybe quarterly. They'll go by and regrease motors, give it a couple of shots. They really don't know how much they're pumping in, how many ounces of grease is going inside, and how often. So you can see, I mean, if you got a lot of contaminants, you want to purge that grease pretty often just to get the old crappy grease out and get in fresh grease. But if your grease is clean and it's cool and not contaminated, you're looking at about a year and a half before you really need to even regrease the motor. This is a big one. I assume this is also something you guys are really familiar with, is overhung load calculations, you know, center distance between shivs, number of grooves, belt tension, all that stuff, really important for bearing life. And if you ever, you know, if this isn't something you're familiar with and you want to go through it, I'd be happy to go through this with you afterwards. It's pretty easy to calculate and keep your customer out of trouble. When we do exceed these recommendations, so when you go through these calculations, it kind of gives you a pass-fail. Yeah, that's too much for that bearing, or no, that's fine. When it's too much, then we have this other solution over here where we go with stress-proof steel in the shaft material and a roller bearing, which gets us a lot higher radial load capability for when you have to have a multi-groove shiv and tons of tension and stuff like that. We can do it, but it's not going to be the standard product at that point. This is just kind of a cutaway of the bearing system here. We kind of discussed all that stuff. So aside from the mechanical, which is like 80% of the failures, then electrical is the other 20. So there's a bunch of different components that can make a motor fail due to electrical, what we call electrical. Now I'll call thermal issues electrical, although you could call that mechanical too. You can imagine there's a motor underneath that, and there's a brake here, and a coupling guard, and a gearbox, all covered in pulp stock, which makes wonderful paper mache, and completely seals that motor, and is like just in its own little cocoon. And you can imagine how hot that gets, and cannot dissipate heat. That's a little Baldor motor. There's a customer down in Longview. They were failing this motor every 3 weeks. That's it. That's as long as it lasted. And you can see why. So the solution there, and I'm not trying to throw Baldor under the bus, but that was just a standard Energy Saver Baldor motor, okay? Cast iron, wasn't the rolled steel their least quality, least high quality. So it was an upgrade to their cheapest product, but it just didn't survive. So we put one of these in, and we're going to talk about temperature rise in a second. And I got to admit, I'm a motor geek. I love motors, and the reason you're going to find out in just 1 second. This motor, it's all about temperature rise. So all motors are rated with an ambient rating. So it's usually assumed to be 40 degrees C or 104 Fahrenheit, right? And most of the time that's about, motors don't live in an atmosphere hotter than that, but not always. I mean, certainly there's when a motor's at the top of a roof and it's, underneath the ceiling, heat rises, the motor's often way hotter up there than it is even on the plant floor. It might be 80, but it's going to be 120 up there. So a lot of different things that can introduce heat to a motor. You might have a high ambient. The motor might be on a drive. A drive tries to simulate a real nice sine wave, but if you look at it, it's a bunch of little choppy spikes that make that sine wave, and every one of those little those are harmonics, and they introduce heat into the motor. So if a motor's on a VFD, it's going to run hotter than it would across the line. So that's another consideration. Is the motor being run overload? I think NEMA did a survey, and the average load of a motor is 103%. Every motor virtually is overloaded. Nobody, at some point somebody designed that thing for the right application for the fan, and then over time people just speed up, and before you know it, whether it's a conveyor, a fan, a pump, or whatever, every process wants to move quicker. That's the desire of all management, and eventually that the motor pays the price. Until you upgrade that motor, it's being asked to do too much. So that also introduces heat into the motor. This is a picture of what we were talking about earlier. This is a motor on start and high-speed photography, so you can see the motor, the windings are actually pulsating, and they're actually moving as the energy is going through it. This is the sort of action that we were talking about that causes abrasion on those wires that tends to lead to a short. So you wouldn't even think that was going on, unless you kind of think about it or get this look inside one. But that's happening to your motor all the time. The worst thing you can do to a motor is start it and stop it. If a motor just, you unpack it, hook it up, turn it on, and left it running forever, man, they go 40, 50, 70 years. I mean, there's motors down in Longview that are 70 years old because they run all the time. The worst thing you can do is turn a motor off and start it back up again. Because every time you start a motor, unless it's on a drive, you're hitting it with huge inrush amps, and you're causing that rotation here of the windings. Over time, if you have a motor that gets cycled frequently, maybe it starts and stops several times a minute, that motor's never going to live. Just can't. It's just too much heat to dissipate if it doesn't run long enough to dissipate that heat, right? So motors that get slammed, start and stop all the time, elevators, those are always oversized a little bit just to deal with that heat. These motors, though, are designed to deal with that heat just in the way they're built. So as we were talking a little bit about that IEEE 841 specification, that specifies as a Class B temperature rise and a Class H insulation. So motors are rated, they have a rise, which is the heat they create when they're operating and producing horsepower. That's the temperature rise. The temperature insulation limit is what the designer has built into that motor, how much heat it can take. So by convention, that IEEE 841 standard says a manufacturer has to build into their motor insulated quality windings up to 100 or 155 degrees C. That's a Class F limit. And it has to run at a Class B, which is 80 degrees or 130 total. We'll get into that in a second. So the difference between that 130 that it runs at and the 180 that it can, or 155 it can withstand, that 25 degrees, is your thermal margin. So the spec has built into it 25 degrees C of thermal margin, which is the best thing you can do to ensure the life of your motor. For every 10 degrees C that you can lower a motor's operating temperature beneath its design temperature, you double the life of the grease and you double the life of the insulation. So this is 25 degrees, so it's 2.5 times. So now you're up to like almost 8 times the life of the motor, grease and winding, and the insulation on the windings, just by operating beneath its design temp. So if I'm a motor manufacturer, the single most important thing I can do to ensure the life of my motor is to design it with a low temperature rise and a high temperature limit. And that's exactly what GE did on this one. So it's designed to run at a B, but it has a Class H limit. So this is all that's required by that specification, 100 degrees C on top of that. So between the two of these, this is 130, so it's going to operate at 130 up to 180. You got 50 degrees now, so it's doubled the amount of thermal margin in it that the spec demands that you have. So what that means in the real world is that motor runs cool, and like I said, heat is always the enemy. The cooler that motor runs, the longer it'll last. The grease lasts longer, the windings last longer. So that's the most important thing you can do to make a motor last a long time. Here's a picture of an infrared thermography that Dave took. You can actually see the heat that the motor generates when it's running. So the components of that, I want to break this down because I think I was throwing out a few numbers that might have confused you folks. You start off with this 40 degree C ambient. That's understood. That's just a given. NEMA assumes that all ambient temperatures are that. So then on top of that, you have the rise. So if you take 40 degrees and then 80 degrees C of rise, and they also throw in a 10 degree hot spot allowance in case you're not measuring the motor at its exact hottest point. There might be a little hotter temperature somewhere. They throw in 10 degrees of fluff. So you got 40 plus the 10 is 50 plus the 80 is 130. So that gets us here to the 130 total limit of insulation limit of that motor. But it actually can go up to 180. So is that kind of clear? Because if there's one thing I want everybody to get today, it's that story. Because that's why people buy these motors. That's the reason. So here's just a couple of, another slide, another motor caked in all kinds of dust. So these are just real world, application issues that you always deal with. Sometimes the ambient is higher than 40 degrees. Sometimes there's some kind of foreign material all over the motor. Might be pulp stock. It might be some kind of dust. Maybe they're running the motor over its design or over its designed load. So it's a 50 amp motor and they're running it at 54 amps, so it gets a little hotter. Maybe it's run on a VFD, or maybe your line isn't balanced right. You got each leg isn't the same voltage. All those things introduce heat into the motor. So the more margin you have to deal with that, the better off you're going to be. Here's a few other things. I think I talked about all of this. Got ahead of myself. This one I didn't cover, contamination. Depending on what the chemical that's on the windings in the environment, there's some chemicals that are extremely abrasive. They actually eat the insulation off the windings. So there are certain things to watch out for. Some contaminants are abrasive. We've got a customer that coats their product in cornstarch, and cornstarch, they're also pumping sugar, and sugar is really abrasive. You'd be surprised how abrasive sugar is, and if it gets inside the motor, man, it just creates havoc. And then the mechanical movement at startup that we talked about, all these things that introduce heat into the motor, they all happen. So that's why it's good to have a motor that's designed to take that. This is a video. Dave, you want to explain this one here?
Yeah, this is inside of a Stator. It's a 4-mile coil, so it's a larger motor, but it's while we're testing it, and we're surge testing it. This motor has a turn-to-turn short, and just what's actually going on when we're testing it is we can see where it's failing right there. And kind of a significant thing about it is that the motor wasn't grounded at all. So, or your meter on resistance, you wouldn't see anything wrong with it. But really in real life, there's a turn-to-turn short. That motor is winding as well. So, but it's just kind of neat to be able to see inside of it what's going on when you're running a test on it.
How do you run that test?
with Baker AWA. I'll talk to you guys about that. So when I get to mine.
What'd you read line to line? Did you see a difference there?
Yes, on the surge test. Yeah.
Well, I mean, yeah, when you were testing the forms, why, it's just because.
Oh, for resistance test. No, I think it even passed that. Yeah, yeah.
So this slide shows a couple of the components inside. We were talking earlier about the bracing, the face paper.
Yeah.
Pardon?
Did that other video not work? Hey, you back up one slide?
Yeah, we just showed it.
I thought there was another one we just skipped over. Or not? Yeah.
Oh, yeah.
Is there something here?
Should be.
This is the GE proper video.
Yeah. You got to tell them about this one too.
Yeah, so this is a video that was done at Oregon State University by a couple of guys that have their PhD in motor science. And what they're doing a study on is what happens when there's an actual turn-to-turn short. So they're going to induce a turn-to-turn short in this motor winding. You can see the motor up here. And I don't know. When they hit this knife switch right there where the light is, boom, now that they just induced a turn-to-turn short while the motor's running. And it's just kind of showing you how long it takes before it builds up so much heat that the motor fails. And why we're showing this is, well, I'm going to talk about testing after Ed's done, but that's why it's good to predict when you have a turn-to-turn problem in a motor, because a turn-to-turn short is the beginning of the end, as you'd say in this, the other video that didn't work. Right? And so you can see it's been about 30 seconds. Hopefully we'll see this. I think real soon you'll see smoke start pouring out of the motor. And and this is a turn short at operating voltage. You can see the smoke now. So when we're testing motors, we're testing higher than operating voltage to try to detect these turn-to-turn issues, to give people a window of opportunity to change out that motor before it gets down to a turn short at operating voltage, because once that happens, you just have minutes until the motor fails. That's basically what I'm trying to show you here. But if we can pick that up, you know, if it's a 48 volt motor, we can see that happening at 1408 volts, for instance. It gives you some time to think about changing that motor out, getting it fixed.
Time is running out. So these are a couple of the components inside. We kind of talked about face paper, of course, copper wire, insulated, varnished. That adds a lot of rigidity to that crown here. Again, that's just basically designed. You want that really rigid. And then the C5 steel that we use here on these really, God, I can't remember the temperature rating on that. It's in one of these slides, but it's high.
I talked about what the.
Yeah. So the Stator is, and I had a slide, but I took it out unfortunately. I had to show a copy of the punchings, but this is the Stator here. These are all a bunch of thin laminations of steel, and punched into those is a design that's proprietary and unique to that manufacturer for that rating. You know, it affects the torque characteristics, the efficiency, the punchings. So I'm a terrible drawer. Well, actually, I won't draw it. This is a cross section of a Stator. So you can see here what I was going to draw, the cross sections.
Tons of lamination.
Yeah, they're just really thin, like maybe a 1/16 of an inch or so of steel lamination, and they've got a pattern to them that defines really the torque, the efficiency, a lot to do with the motor. All of its performance characteristics are really all right here. And then the windings go through that, insulated with slot paper in between there.
It's really hard to tell when you look at it. It looks like a solid piece of metal, but it's really hundreds of thousands of those stacked on top of each other. Each one of them has insulation on the metal.
Yeah.
They're just pressed really, really tightly together.
So I want to talk a little bit about selection on an application. I would assume for the most part when you guys are replacing a motor, you're going same for same, right? I mean, pulling out a 25, putting in a 25. So I think, you know, you probably know, from my point of view as a motor guy, if I'm replacing a motor, this is the stuff I want to know right here. What's the horsepower, RPM, volts, frame, enclosure? If you've got a manufacturer part number, a Baldor EM 3711G, that helps because then we can, find that exact one or cross that to something that we have on the shelf. Also, if you could tell us if it has any special features, heaters, thermostats, RGDs, an encoder, anything like that, special bearings, roller bearings, that's something that we want to know to make sure we select the right motor. And then we usually want to know if there's anything unusual about the driven equipment. Is it a pump or a fan or a conveyor? Because that tells me what kind of load it's on. Is it on a VFD or is it across the line? Is there any unusual failure history to this equipment? I mean, are you replacing this motor regularly? Then we got to look at, upsizing the horsepower or why it's failing and kind of come to a more intelligent solution than just replace. That I love doing that kind of stuff. So where you've got motors that are failing and everybody's scratching their heads, let me know, because he and I just live for those kind of applications. So a lot of this stuff you'll get off the nameplate, some you won't, like the load, because the manufacturer wouldn't know that, right? So they wouldn't put that on the nameplate. So if you can tell us a little bit about if it's on an unusually high inertia fan or anything like that, a hard to start compressor, those sorts of things are helpful. There are different motor designations, and we're going to talk about that in a minute on torque. And this is a sheet that can be of use when you're trying to, a little data sheet to help you collect the right information. Along with that it's got, is it started across the line? Do you need drawings? Does the customer want submittals? That sort of stuff. You can fill all this out, send it in to us. This is some look at some nameplates, just various brands here. There's stuff that all manufacturers will put on a nameplate, and there's things that aren't required. We put on all of ours the bearing numbers. Not everybody does. I was down at a customer site last week where the guy was having a hard time identifying what bearings go in the motor, and so I was helping him do that and realized, wow, none of them are marked. That's unusual because I'm used to working with GE and we always put the model numbers, the bearing part numbers on the nameplate. It makes it a little difficult when you're trying to replace a bearing and you got to open the motor to find out what bearing's even in there. This is a picture of an IEC nameplate. I don't know, do you guys see much IEC stuff? Is it mostly NEMA?
Yeah, it seems like so.
Yeah. We see some IEC stuff on driven equipment that comes in from Europe a lot in the process industry. So one of the things that we excel at is switching this stuff over to NEMA frame stuff because these are hard to find. They're metric dimensions. They require metric tools. They're not commonly stocked in the U.S. If we were in Germany, you could get that all day long easily, but not here. So most of my customers want me to yank these and replace them with a NEMA equivalent. And there are some differences. The frame sizes are different. That's, I think, one of the advantages that we bring to the party is we got a mechanical PE on staff who spent his entire life in a paper mill on the reliability side, mechanical engineer. And what he does, in addition to lots of things he does, one of the things he does for me is when I'm replacing these metric motors with a NEMA standard, he'll draw me up a nice base that makes all the mounting hole changes and a plate so the motor is mounted on that plate. Then when the customer goes to install it, they just put the plate and the motor down, pull the old metric, slap in the new US NEMA dimension motor, good to go. We already make all the shaft dimension differences. There'll be the right pulley on there of the right diameter of the new shaft, so you won't have to pull a metric shaft pulley and try to adapt that with the new bushing to this. So just really, our goal is to make it easy when a guy fails a motor to put in the right quick replacement. So this is just a look at a GE nameplate. This one here is, we talked earlier about the adjustable speed drive rated motors. This is one of those. And I can tell because when I look at it here, it's got the horsepower. So this is its motor's nominal RPM, 1800. This one can be overspeeded to 90 hertz. So it's got a 90 hertz, there's the 2700 RPM, and the amps at that, and then the amps at 1800 at 60 hertz, and then the amps horsepower at 0 speed, 7 volts. So you've got data all the way across the speed range of this motor. Tells you it gets constant torque from 0 speed to 1800, constant horsepower from base speed to 2700. Gives you a lot of different, PWM type drive, the weight of the motor, a lot of good information on there. A normal motor that's not an adjustable frequency drive motor won't have that additional line, this line. It would just have that, the 1800 RPM because it's not designed to be operated above base speed. So that horsepower number is what the motor is designed to develop. Now, motors are stupid and they'll do whatever you ask them to do. So if you're asking it to do 250 horse or 300 horse, it doesn't really know the difference. It will just, when you demand, it will give until it can give no more. And that's when the smoke starts coming out and everything else. So we have a friend who always said, motors can't read their own nameplate. They don't know what they are. So it's important to stay within the limitations. This is that little formula. I gave you this one before. There's also a little cheat sheet. If you're dealing a lot with 3,600 RPM motors and you're curious what the torque is on those, it's 1.5 times the horsepower. And then all the way across down for sludge feeds. RPMs, of course, that's going to be on there. That's on everybody's nameplate. This is that formula we showed you earlier, 2, 4, 6, 8 poles. And then the actual speed. So this is a synchronous speed. This is the nominal speed here, actual speed, 3450. The difference is slip, and we're going to get into that in a second. So what's happening when the motor is running is, you know, we start a magnetic field rotating. You know, the very first slides we showed with the cross section of that 60 hertz cycle across the way. All that's really doing is setting up a rotating magnetic field that the rotor is trying to catch the entire time. It never does. It always lags slightly behind. That amount that it lags slightly behind is called slip, and it's that attraction that produces torque. If those two were locked together, there'd be no torque. They're just rolling around together. The fact that that is always behind and chasing, that's your torque producing element. So that's kind of what this is showing us here. So the difference is called slip, and you can refer to that motor any way you want. You can call it a 3450 or a 3600. I'll know what you're talking about. Anybody would. And then the voltage, that's always on there. Frequency, that's always on there. Usually going to be 60 though. And then the amps, that's always going to be on there. So those first 5 things, all manufacturers are going to give you. After that, there's a lot of stuff that not everybody puts on there. NEMA Design A is the inrush profile of the amps that it draws when it's starting. KVA code letter, same, or NEMA Design A, I'm sorry, is torque. That's KVA code letter.
And we talk about A, B, and C and why that might matter to these guys?
Yeah, there's a slide here. So this is your basic speed torque curve. So here we are at 0 speed, and this is 1800. So when we start our motor, we have to produce the amount of torque to break it away, then it drops down a little bit, then it gets to the most torque it can produce. Below that, it would drop off and go to 0 speed. So there's a lot of different lines here. But let's just assume here we are starting. So when we go to start the motor, we get 150% of torque right when we go to start. It doesn't last long, just for 15, 20 seconds, so long enough to accelerate the load. Then it drops down. The lowest point on that curve is called the pull-up torque, and at this grade, it's 125%. And it goes back up, and this is where, at this point, this is the most torque the motor can produce. In fact, it can't produce it very long. It drops back down here to full load torque. If you keep loading it up, it goes to 0 speed. So if you overload it more, it just stops. So there's 4 different letters that define torque in a motor. They're called the NEMA Design. NEMA Design A is, I think a lot of your loads are kind of NEMA Design A to me. They're fans, easy pumps, centrifugal pumps, and all of our motors are suitable for A. Because A is kind of the easiest, and this is what the torque looks like, the speed torque curve. B is what's considered standard. So these are NEMA B motors. So the way it works, if it's a B, it'll do everything beneath that. So it will do A. If it's a C, it will do B and A, like that. So NEMA Design B is normal breakdown torque. It looks like this. It has a little bit lower starting torque than the A, but it has correspondingly less current too. So it doesn't draw as much current, because current and torque are proportional. If you need a lot of torque, you got to have a lot of current to do it. So this has a little less current on startup. It's just a normal, what they call the normal profile. It's usually about 2% slip. They're just defined as normal duty motors. Design C, you'll see those a lot on hard to start compressors. You usually see them up around 200 horse and above. I don't think I've seen a lot lower than that. You might, but generally they're in the larger horsepowers. They have kind of an unusual starting torque curve. They give you additional starting torque at the beginning, but they don't give you as much breakdown torque at the end. So these are really used to start hard to start applications like chippers, anything that's got a lot of inertia that you're trying to start. You see a lot of NEMA Cs. The last one is NEMA D. NEMA D is the highest starting torque, up around 300, 275 typically, and its curve just drops off like that. These are elevator motors. You see these a lot in elevator motors. Some centrifuges, things like that. Again, really high inertia, really high. Service factor, every motor is really, almost all motors are 1.15 service factor. All motors are 1.0 when operated on a drive. So if a motor has a 1.15 service factor, that means that you can operate it at 115% of its rated, nameplate ratings without causing harm to the motor. Now, that's the NEMA designation. I'll tell you, if you overload a motor 115%, unless it's one of these, you're not going to be overloading 115% for very long. Certainly not indefinitely. And even one of these, I wouldn't want you to do that very long. I mean, you really need to correct, size the right motor for the right application. But these are designed to take the overload that most won't take. So just keep in mind, any motor on a drive is 1.0 service factor. You no longer have that headroom. You can't get 11.5 horse out of a 10 horse motor when it's on a drive. You're just going to get 10. Okay. Frame size, that's really important. We're going to talk a lot about frame sizes here in a second. That's a NEMA standard. All manufacturers have agreed to use, like everybody's 5 horse 1800 RPM motors are 184T by standard, no matter who's the manufacturer. So that makes it really easy if I'm replacing a Reliance or a Baldor with a GE or vice versa. It's all interchangeable, with a couple exceptions. When there's something different on the motor, they put a frame suffix on it. So you might have seen this. So like, let's just say 254T, that would be a normal motor. If it's a 254TC, then it's got a C-face flange on it. I've got some pictures of these things if you guys aren't familiar with some of them. A Y indicates non-standard mounting. Doesn't tell me what's non-standard about it. Just means be careful. This one's non-standard. I've seen some Ys that literally are round frame motor with no feet. So they're just mounted off the driven equipment. So that wouldn't be a problem normally if I gave a guy a motor with feet. You just wouldn't use them, right? Well, sometimes that might be a problem if you've got a space limitation or something like that. So anytime there's a Y on there, I want to take a look at it. I want to physically see the application, see where the motor goes, what's weird about it, is there room, is there a space limitation, is it a double shaft? Because people use Y, even though Z is the non-standard shaft designation, I've seen Y used for double shafted motors. I don't know why, but people do. So there's all kinds of different Ys. They can mean anything. A D flange is a lot like a C face, except there's bolts that go through the flange. It's a small difference. And these are all vertical frame designations. JP and JM are close coupled pump. The shaft has several steps in it, and they go into centrifugal pumps. And there's more than this. These are just the common ones.
Do those vertical pump motor?
Yeah.
Are those built different, like you were talking earlier?
Yeah, quite different. So they're designed, of course, to be operated vertically. They're either available solid shaft or hollow shaft, where the hollow shaft, the pump shaft, comes up inside the motor and is coupled up on top of the motor. Kind of an unusual situation. And then they're just designed, just for water, wastewater is typically where you see those. Predominantly vertical motors, pumping chemicals and water, typically.
And a lot of them are designed to hold the extra weight of the driven equipment.
They have thrust bearings on them because a lot of pumps will pull down. The impeller design pulls down on the rotor or pushes up on the rotor, depending on which way it's running and what the pitch of the blade is. So you got a lot of additional stuff going on in vertical motors. You have that referred axial thrust coming back or down from the pump or fan, plus the weight of the rotor. So they commonly have thrust bearings in them that can take some pretty high thrusts. The weight of the rotor plus another 75% for the up thrust from the pump or whatever driven equipment. So they're definitely a little bit different animal. We do a lot with verticals, but I'd say probably 80% of what we do is horizontal.
Yeah. One consideration if you were ever changing bearings in a vertical hollow shaft motor particularly is sometimes we'll see multiple thrust bearings in the drive end of a vertical hollow shaft motor. And the orientation there is really important. As Ed mentioned, you get motors. You're holding the weight of the shaft and the impeller, but you're also trying to deal with the up thrust. And so you'll see a configuration where maybe they're back to back or front to back, and so it's just really important that if you were to ever get into the top end of a vertical motor, that you're marking and noting what orientation those bearings are in, because if they go back in the wrong way, you get some pretty screwy stuff starting to happen. So just a little food for thought there.
Do they have to be pressed in? I mean, you have to have so much torque and you press them together, or
No,
or is it just you just slip them on, you just put color on?
Yeah, I mean, you heat them, hopefully with an induction heater, and it would go back in like you see in a horizontal motor, except that the orientation is much more critical. They're marked, so you know that they're not marked, no, but they do come apart. It's like a two-piece bearing, so it's the way they come apart is.
On a bigger one, we do have to jack it up from the bottom though and set the end plate, so we got to squish those bearings together.
It's really something that from a liability standpoint, you probably don't want to do in the field. But customers ask us to do crazy things sometimes, right? And so that's something for you guys to be paying attention to.
You guys want to take a little break for a minute? Or?
Yep.
Yeah, 10-minute break?
Yep. Yeah, what's that? 50 horsepower. It's
Okay, so let's continue here. We're going to talk about frame sizes. So I don't know how many are aware. Probably nobody in this room was working pre-64. I don't see anybody that old. So these are the original NEMA motors. So from the beginning of time, since Edison and Westinghouse, turn of the century, till 64, there were no, they were all the same frame size. So that, I'm sorry, original NEMA, till 52. I got that backwards. So original NEMA goes from like turn of the century to 52. So that's all these frame sizes. In 52, they did a U-frame re-rate. So you may have seen U-frame motors. There's still some of those out there. They stopped making those pretty much in the 70s, but it was an old design. It was real popular, really rugged, beefy, heavy-duty motors. The industry kind of wanted to get away from them because they were just really expensive to make. So they re-rated to the T-frame in 1964. And when T-frames first came out, man, they were just hated in industry because they were just so much less rugged than the U-frames that, they were replacing. And the problem is, and this sort of bites us, as, I keep using the word NEMA, which is National Electric, Motor Association, Manufacturers Association. Oh, close enough. NEC, right, in your world, the U.S. codes, right? Versus IEC, metric, that side of the world. Our stuff is robust. It's designed with overload into it, service factor, extra load, extra capabilities that the IEC devices just don't have. So if you're, using an IEC starter, the contacts are tiny compared to a NEMA starter. They're like 4 times as big on a NEMA starter. So it's not that they're bad. They're just application specific. If you've got a 10 amp motor, you got to use the 10 amp IEC contactor. There's no range like there is on the NEMA side, right? So as long as you design your system correctly and put the right motor in there and never asked it to do more than it should do, all that IEC stuff is great. Starters, contactors, motors, blah, blah, blah. But in the real world, that's just not how it is. Stuff gets overloaded and people like rugged, heavy-duty stuff. So that was a knock on these motors when they first came out in 64, was that they were just kind of light duty versus the stuff they were replacing. Those U-frames had a reputation as just rugged. They were designed partially by the U.S. Navy for mil-spec work. They were designed to live on the decks of battleships, get wet all day long, and they're just and never fail because you just can't have a failure, So that's in the automotive industry used them a lot too. So they were designed with really high standards, heavy motors. The T-frames came out. They went to aluminum frames. So instead of cast iron, this would have been an aluminum body, which is great. Sometimes when you're having to carry it up a ladder or up 14 flights of stairs, it's nice to have a motor that weighs 70 pounds instead of 110. But the industry didn't like it. Aluminum doesn't hold up well in certain chemical environments. It gets eaten up by salt and other things. So the T-frames, we are still on the original 1964 re-rate of T-frames today, almost 50 years later. They've done a lot to beef it up. They've gone to cast iron, so you don't really see aluminum anymore, unless somebody's really making a low-cost motor. These are a lot like the old U-frames used to be. With that B with H, that thermal margin story, that was really typical of all U-frame motors. All U-frame motors had that kind of thermal margin built into them. The T-frames just didn't. When they came out, if you asked it to run a little higher than it was designed to run, you're in trouble. Your motor's getting hot and it was going to fail. So over the last 50 years, they've beefed up that design. This 841 is an awful lot like the old U-frames. The main difference is these frame sizes are all dimensionally different. So if you've got a motor from the U-frame era, and this still does happen because there's still an awful lot of these out there. Now they're old now. I mean, they've been obsolete since 1964. So if you find one, it's 50 years old, right? And that's the proof that how good they are. They're still out there. But when you go to replace those with the current frame equivalent, so what I've done here in this chart goes by horsepower and RPM. So at any given horsepower and RPM, so let's just pick a common 10 horse 1800. In an original frame, it's a 324. In a U frame, it's a 256. In a T frame, it's a 215T. These are all different dimensionally. They have different foot-hole mountings. They have different shaft height. They have different, well, they do have the same shaft diameters as long as you're in the same horsepower. So they make transition bases for these, though, that you can take a U frame, put it on a transition base. It brings the shaft height up to the right height for a T frame. The shaft diameters and lengths are the same, so your pulleys are still going to fit. It's mostly what they call the 2F, which is the length on the holes, and the 2E, which is the width on the holes. Those are different. But they make a transition base that makes those adaptions, so you can make that work. There is no transition back from this to this, and this transition from this to this has been obsolete for a long time. But for a while, they made transition bases for those motors, too, from U-frame to original NEMA. But this is where we are today. Almost everything you see in the field is going to be a T-frame motor.
Let's talk about what the frame means and kind of some of the problems we see with guys. We'll get a call, right, and somebody's installing a motor, and we'll pick Ed's 10 horse 1800 again. So they've got a 215T motor, and we'll get a call, and it doesn't fit. Well, a 215T is going to be the same across all the manufacturers in some cases. Your bolt hole pattern for the feed is going to be the same, shaft height, shaft diameter, usable shaft length. But then there are some things that aren't NEMA standard when you're looking at the frame. So the overall length is one that we get into trouble with a lot. You get a replacement motor, the premium efficient designs, which now impact another segment of motors, verticals, crusher duty. There's some other things that are impacted by it. Some of the manufacturers have compensated and made those more efficient to meet those regulations by making them longer, and so we run into that a lot. So it's something you guys probably, will see in your careers at least once, where you're trying to replace a motor and this thing doesn't fit. I've got the wrong motor, but if you've got the right frame size, you don't. And what we're starting to see is that with some of those changes, we actually have to modify the location of the installation sometimes. Another way guys get into trouble, dual drilled rear feet. So you'll have a motor that's drilled for two frame sizes, right? So a common one with a customer of mine is 200 horse 1800. It's drilled for a 445 and a 447 T frame. So the 2F, the length from front to rear holes, is what, it's 11 and, is it 9 and 11?
That's about that.
So something like 9 and 11. Well, there's some original installations where maybe somebody drilled to match the wrong sets of bolt holes, and so you'll find something that maybe is non-standard. So there are guides out there, and we can send you links if you email Ed or Dave to a frame chart so you can see what those dimensions are. But it's some of the ways that the guys still get into trouble, but remaining in the same frame size. So while things are interchangeable, there's still some considerations to have when you're out there in the field.
The two biggest gotchas are the length of the motor, like you mentioned, that's the C dimension. So if you've got, that's from the back of the motor to the tip of the shaft, that's your C dimension, overall length, right? So if you've got a tight spot, then you've got a piece of rigid conduit back here, and you're trying to, probably let me know, because there could be a 1/2 inch to 1 inch variation on motor length between manufacturers, sometimes more, depending on the size of the motor, right? On a little one like this, it might be 1/4 inch, 1/2 inch, but on a 200 horse, it might be 2 or 3 inches, right? Significant, it may be even longer. So if you've got a space limitation issue on the length, let me know. The other thing that's not a standard dimension is the overall diameter of the motor. The shaft height and stuff is, but the diameter of the frame could be longer or wider or smaller. Reliance particularly makes very skinny, long motors. So if you're replacing a Reliance, you might, and if it's a tight spot, another motor might not fit in there. So you might see that occasionally. So if you're replacing, what should be just a standard, frame for frame, it'll be great unless you've got unusually tight space limitations. Most people wouldn't put something up a wall, 1/2 inch away from the motor, but it happens, So if it's really tight like that, then let us know. Otherwise, you probably are going to be okay. But All the other dimensions are going to be standard. It's just the length and the diameter that can be off slightly.
The last thing about frame sizes, a lot of guys, and I wondered this at first, what do those numbers mean? Is there any meaning to them? And there actually is. The first 2 digits divided by 4 is the shaft height. So when you look, I'll pick an easy one because I'm stupid. So if we look at like a 449T frame motor, that's an 11-inch shaft height. So that dimension you're able to figure out. So if you're ever in a situation where you're trying to figure out what your shaft height is, or you're looking at a motor in the field and you're maybe not sure what your measurement is, because it's always hard to figure out with a tape, with a coupling guard or a pulley or something in service, that number divided by 4 is your shaft height, which helps kind of steer you to the right frame or right motor if you're not quite sure what you're looking at. The last number doesn't mean anything.
Yeah, that works all the way through. So, even here, drive by 4, 3.5, all the way to the big ones. So we talked a little earlier about those frame suffixes, like 254TC, this is a C face. Commonly that'll go up to a gearbox or a pump or, any driven equipment. This is an example of some non-standard shafts. Obviously this one's got a bunch of steps in it and stuff. There's a variety, of course, custom applications. This is a JM or a JP close couple pump motor. You see it's got a step here in the shaft, and it's also got a threaded hole here for the impeller, the pump impeller to go on. So insulation class, back to nameplates here, class F, that'll be on the nameplate. All manufacturers have to put that on. Oh, geez, this would have been nice to talk about when I was adding everything up earlier. So the B that we were talking about earlier, 40-degree ambient, 80 degrees rise, plus a 10-degree hot spot is your 90 for a total of 130. So for the 4 classifications there you can see. So we were talking about with the B with H, it's this pattern right here, 180 and 130. And it's also interesting, they claim 90, over half the ratings are underneath a class A rise. So GE's is pretty conservative. So they don't say that, but when they actually do the tests on these, they're actually half of them are class A with class H insulation, which blows my mind. In the enclosure, this one's TEAO, totally enclosed air over. So that motor's mounted in the airstream. Unlike this one, which has a fan on the back and a fan cover, this motor has no fan and no fan cover, and it is only going to cool by being mounted in a plenum where air's going over it. If it's not in that situation, motor's overheating. These are the real common enclosures. Open drip proof, I'm sure you guys see a lot of those. Those are open, as the name implies, free exchange of inside and outside air. So not good in a hazardous location, explosion proof, not good in a dusty or wet environment. But if it's clean indoors, that's they cool themselves better than a TEFC motor, so they run cooler, so they last longer. So I like open drip proofs in clean, really clean indoor applications. Anything other than that, you really need to be looking at totally enclosed, either a non-vent, totally enclosed non-vent. You don't see a whole lot of those. Those are usually time-rated motors, like 60-minute duty. You see them on cranes is a good example, that you can only run your crane for so long before it gets too hot. But they're not usually run all the time. If you have a crane in your shop, you use it to move something and it cools off for 15, 20 minutes and you can use it again. So they're duty cycle rated. And then TEFC is by far the most common enclosure. That's what we've got right here with the fan on the back. And then TEBC is the blower cooled, like the other one I was explaining with the adjustable speed drive motor, where it's got basically a little pony motor that sits on top that has a fan and a blower that blows air into the frame of the motor, or over the frame of the motor. Picture of an ODP here. So it's this one has vents on top. So what NEMA says, if it's an ODP, water coming in at less than a 15 degree angle from vertical won't get in there. So if this water's coming in more or less straight down, it won't get in there. Up to 15 degrees, it won't get in there. If the water's coming in at 90 degrees, it would get in there. Not a good application for an open drip proof. This is a picture of a TENV. See, no fan on the end, no fan cover. Of course, there's a fan. Picture of the blower on top of the adjustable speed drive motor. See these a lot in DC machines too. It's a little unusual on the AC side, a lot more common on DC. And then there's some other enclosures for applications. If it's a wash down, they make FDA approved paint, food grade. We've got a customer that makes vitamins. They have to use wash down FDA white paint or stainless steel because they can't have any chips of paint falling in the process because it's food. Explosion proof, we see those, grain dust, refineries, lots of things are classified and require special explosion proof motor. Just a note on that. So NEC code is, there's two types of classifications, Div 1, Div 2. Div 1 is explosion proof, Div 2 is not. This is a Div 2 motor. As long as the skin temperature stays beneath 200 degrees C, I can put that motor in a Div 2 location. So Div 2 is dust, and so what that's saying is if dust lands on this motor, the dust that lands on that motor has an ignition temperature higher than 200 degrees C. And I know because of what we just went over, this motor only its top is 180 C. So I know at 200 I'm safe. So, coal dust, grain dust, any of that kind of stuff can be, that motor is suitable for that. As long as it's underneath 200 degrees C, you can use a TEFC motor in an explosion-proof Div 2 location. And then totally enclosed air to air cooled, totally enclosed water to air cooled. Those are big machines, thousands of horsepower. The reasoning there is when you just put a fan on the opposite drive into the motor and it's blowing air across, if it's a big motor, maybe 7 or 8 feet long, by the time the air gets over here, it's already warm. It's dissipated heat across the skin of the motor, and it's not cooling this bearing nearly as well as it's cooling this bearing. So a totally enclosed air-to-air heat exchanger is a top-mounted device that sits over the motor that blows air over both bearings and then out through either the sides or the bottom. So they just get better heat dissipation on the really large motors where a fan just wouldn't do it efficiently. And then there's WP 1 and 2. Weather-protected motors are similar to open drip-proof motors in that there is a free exchange of inside and outside air. Unlike on these, there is not. Those are larger machines, again, thousands of horsepower, and Type 1 and Type 2, just two different weather protection grades of that mostly open type of motor. A lot less expensive than these versions is why guys use them. If it's, again, relatively clean, then you can go that route. So, that's what I got. Any questions? And Dave's going to talk in a minute, so we're not done. Dave's going to talk motors, and safety, and testing and stuff.
A lot to process.
Yeah. Well, if you've got any questions, I give you all my card, so email, phone, whatever. Be happy to entertain questions or go on calls with you guys. If you got weird applications that you want another set of eyes on or anything like that, I'm available. So I get up here maybe once a week. So, thanks for your attention.
Thank you.
So bright.
One, second, third, we got 3 of them. Are you using it? Yeah, we should have put them on short at some point. Well, yeah, we're just well, not from Harbor Freight. Perfect. Fine. We found a cheap location.
So my name is Dave Olinger, field service manager for Northwest Motors. I've worked for Northwest Motors for almost 9 years, and I'm going to talk to you guys a little bit about motor testing and electrical safety. If you have questions as we're going through this, just interrupt me, and we'll just handle the questions. Don't worry about that. Do you guys do much motor testing? Troubleshooting, a lot of it, or just a little bit?
Yeah, I mean, we do a lot of maintenance, and then I brought in our 2 standard like meggers, 1,000 volt, and then the older Christmas tree looking 500 volt.
We're mainly dealing with Veggers and multimeters then, for the most part. Okay. And how about vibration? You guys do vibration analysis?
We have an augury tool that we're kind of testing out right now, but I don't know that we have anything else yet.
What do you call it?
Augury. It's a manufacturer. It kind of looks, it's like a pin looking thing. And,
Vibration test.
Oh, vibration pin, yeah.
yeah, but I haven't even used it. Have you used it, Matt?
No.
It's good for like giving you a overall vibration.
Yeah, it records the vibration and it puts itself into like a spreadsheet of some kind and gives you like a report. But like I said, I haven't used it.
I think it's useful for training. You know, like you did it one day, came back in a week, and
Yeah.
again, could use it for that. You guys do any thermography, IR
Our
type stuff?
electrical department does some. I don't know that anybody in the field, HVAC field, has one at this point.
And probably no online motor testing then? All motors are running electrical testing? Okay. Just getting a feel for what you guys are used to dealing with. So first we'll talk a little bit about safety. Here's a good picture of an arc flash. Have you guys all been arc flash trained or to some extent are familiar with?
Everybody's got Cat 2 arc flash gear on their trucks, and then we have Cat 4 in each zone.
It's nasty stuff. I've seen a lot of the aftermath and some small arc flashes in person, and it's no fun. So it's a real thing, and I just want to emphasize that always be careful. Always want to go home at the end of the day, right? So just a few things here, some self-control questions that I like to tell people to think about before they jump headfirst into an electrical cabinet and start trying to test things. It can, like I said, help you make sure you go home at the end of the day. Do you fully understand the scope of the task? You know, I'm mainly talking about testing and troubleshooting, stuff like that. So, are you trained and qualified to perform the task? Have you done it before, or have you talked to your supervisor, coworkers, or a trained professional, which be somebody like us? So, basically, the point I'm trying to make there, if you don't know, make sure you ask. And you guys all have my card now. Any questions, you can just give me a call anytime, day or night. I'm used to it, and I can hopefully walk you through it or come help you if you need it. Always think about the possible hazards associated with what you're doing and people around you. I went into a motor control center a couple months back after an arc flash had happened, and it was on a pretty large medium voltage motor, but still it actually, the motor control center doors are designed to withstand an arc flash if all the latches are bolted down, and even though this one had bowed all the way out, and there was a light inside there with a halogen light, with like a quartz glass front on it, and that glass actually melted and ran down the wall. So it's gnarly. Of course, make sure if things are energized or not, all your exposed conductors. You guys carry the fluke pins and okay, good. And then also, make sure you have the right PPE, and you said you have level 2 stuff.
Yeah, everybody's got Cat 2 on their trucks.
And you guys do much energized troubleshooting while things are running, or mainly always firing? Yeah, I saw you sometimes. So just be aware of what. Yeah, good. Sometimes you can't shut them down, right? And then use the lockout tagout device. And then safe approach distances. A lot of the newer stuff will have labels on the doors that tell you, what category of clothing that you should be wearing and what that arc flash boundary is around the equipment. And then, I'm sure you guys work at all different kinds of places, so I'm just kind of saying, make sure you have the right permits for wherever you're at. And then we'll get into the guts of the thing. So, motor testing, there's lots of different technologies out there. We're going to be focusing on the electrical side of it with this presentation. But so there's vibration analysis, which is really good for, you said you have a vibration pin, but it's really for, strong for the mechanical side of things. It's why we like to see another reason we like to see the bearing information on those nameplates, because if you have a good vibration program, you're entering in the bearings for the motors that you're doing the vibration on, and you can tell if you have bearing issues, before they actually fail on you. ball spinning, based on whatever you enter in there, based off of those exact bearing sizes, we can tell you if the bearings are failing or not. So that's really good. And you can see things like misalignment and mechanical looseness, soft foot, all that kind of stuff. So vibration is pretty strong. I definitely recommend it. Oil analysis, but it's mainly for bigger motors that have oil bearings. Thermal, the electrical side of things, you can see if you have, the motor's running too hot, of course, with the bearings, and then it's really strong for inside the electrical panels, finding loose connections, that kind of thing. And then electrical testing is what we're going to talk about. So when it comes to testing your insulation system, looks like you guys are all familiar with and have digital multimeters. So
does everybody have the X-Tech 1000 volt? Is that kind of the standard that everybody has?
That's the measure you have?
Yeah.
So one call that I get a lot is people will call me up and they'll say, I have a problem. My motor's not running. I went out and I tested it with my Megger and it's good, but it still won't run. How could that be? Well, the reason is with a Megger, you're just testing to see if a motor's grounded or not, right? Do you guys get that? Yeah. So we're testing to see if a motor's grounded or not.
Sometimes it's cold when you do it, so it doesn't.
Yeah, but
give you the conditions.
it's not testing that turn-to-turn, phase-to-phase type issues. That's to do that, you need to do a surge test, and it's nothing that you can do with a Megger. So I mean, don't feel bad, but just know that all it's really doing is telling you if the motor's grounded or not. And you can also see if you have a complete circuit or not. If you go from one phase to another, they should, this should read really low. But and then resistance on your multimeter, you could do phase-to-phase resistance to make sure that you don't have an open circuit. But really, you're only going down to 1 decimal place on a handheld multimeter, and that's not accurate enough to tell you if there's a winding problem. You need something like with a Kelvin bridge in it with more accuracy. So the next another test people do is a high pot test, but so it's kind of like when you take your Megger up to, if you have a 480 volt motor and you go up to the 1000 volt scale, you're putting higher than the operating voltage on the motor and seeing if it breaks down at that point. So if you passed at 480 volts at 500, then you take it up to 1000 volts, and maybe you're starting to see that maybe the reading doesn't look so good. It's giving you, it's telling you that there's some weakness there. And then a surge tester is what I was talking about before. That's how you check for those turn-to-turn, phase-to-phase type problems, and that's something that you don't want to exclude when you're out there testing motors. If you have a weird problem going on, you'll want to call somebody to come and help you, like us. And we use the Baker AWA. Have you guys ever seen that before? Mm-hmm. So we should probably set something up. I could come show you guys a demonstration of that, show what it's all about.
So like a floor-mounted.
It is. So
you had a photo of it. That first.
Yeah, it's. Like that.
Nope.
Okay, right there.
Break out your checkbook, Seth.
Yeah.
Yeah. So you don't even need to do that because you have my phone number now, and we have a couple of them, and spend a good deal of my time just running around helping people with motors.
So how much do you charge? I mean, are you charging 1, 2 hours, 4 hours a day?
Yeah, it's usually hourly plus travel, and I don't know if he's giving you our rate sheets yet or not.
So we kind of break it up to about 4-hour increments. So when we go out, we charge half a day. Which would cover maybe even coming up here and back in a lot of cases. But
Are you guys up in Seattle often, once a week?
Yeah, well, we just
all the
picked
time.
up Phillips 66, and Boeing asked us to bid on their contract as well. So I think we're up here a lot more.
Yeah.
I test the motors for the City of Everett drinking water plant at least once a year. Doing that, been up there installing cool blues, stuff like that. So
yeah, so we're up here an awful lot. And then we have a couple, actually our double E is up here in Seattle, and he's available. He actually runs around a lot with Dave and does cool blue stuff. And then we have a controls engineer that works up out of Redmond. So we've got a lot of resources up here. But the test equipment for the most part lives down in Longview or in Dave's truck.
Yeah. So if you have a customer that's cares more about their stuff than just run a failure, they want to do some predictive type maintenance, then this is another reason to use this kind of test equipment or have us come and help you. I do a lot of routine testing for people on their critical motors, because when you test with this, it it does the lead-to-lead resistance test with a Kelvin bridge, so it gets down to really accurate resistance readings. And just that first test alone, I could tell if the winding is not balanced, that there's probably going to be a problem there. I think you asked me about that earlier when we were talking about testing. So if you just use your fluke meter, it's going to say like 0.1, for instance, phase to phase. But when we use a tester like this, it's going to say 0.1, 2, 3, 5 or something. And all three phases need to be within 3% of each other to know there's a problem. And a lot of times we're testing from usually we start out testing from the VFD or from the starter. So if everything's good, then you're cool. But if there's a problem, then we would go to the motor, disconnect, test the motor itself. And that way we can tell if the problem that you're having is in the leads or in the motor itself. But this type of test equipment saves all that data. It saves the resistance values, saves the megohm values, the PI, the surge test, everything. And then when you come back a year later, say, and test again, you can see if the motor's overall health is staying the same or if it's degrading over time. And that's one of the powerful things about using that kind of testing technology.
I have a quick question. Is the size of motors dependent on when you guys come out and use those? Like, would it have to be, say, 20 horse or more? Or?
Well, I mean, just on your part, it probably make more sense, to not have me come and test a 1 horsepower motor. Because you can just swap it out so easily.
There's a really wide school of thought here. So we just did a turbine generator outage with a customer, right? So we were testing motors on this turbine generator that really don't make sense. We were testing a $250 motor. It almost costs as much to have Dave out there to test this motor as it does just to replace it. But if that motor fails, it's a lot more expensive than the cost of Dave. Much more expensive. Gummy Bear Vitamin Factory that we deal with a lot down in Portland. A lot of small stuff, but if they lose that process, it is really expensive. And so a lot of times where we're doing these testing routes, annual, quarterly, whatever the frequency is because it's a critical to a process. So it's almost more that than it is the size. Though once you get to a point where motors aren't throwaway anymore, again, there is a point at which you can kind of save a motor by reconditioning before it goes over the cliff and becomes a rewind or a throwaway. And so that kind of comes into play with horsepower, and that's probably around 100 horsepower. So is that?
Yeah, it seems funny, but based on how critical that motor not going down to them, it has a lot to do with it. Like you said, that Gummy Bear place, they have me out there testing 3/4 horsepower motors, but their downtime is thousands of dollars an hour, say. So it's huge to them.
So is this is when the motor's down, do you also have a test when it's running as well?
I do, absolutely. Yeah, but it's apples and oranges kind of.
But do you want them to be able to do both on the same day?
Sure, if you can do both, it's your best bang for your buck for sure. And the test is called a dynamic testing, and this is called static testing or offline testing. The live test is what we call dynamic, and it is like a full systems test. So I'm hooking up to all 3 phases and monitoring the voltage and current on all 3 while the motor's running and checking for harmonics, under, over voltage, current imbalances, using the motor as a sensor and checking the load, so the fan or the motor, and seeing if there's any kind of weird mechanical problems. So it's a good test, but it's not testing the insulation like this is. Yeah.
When you're mating, you want a hot motor, you don't want to get one that's been off for a while.
Ideally, to give you that better idea of what it's going to be like, then again, a tester like this does a temperature compensation to 40 C, which is what he was talking about earlier. That's what the industry says motors should run at. So this tester will tell you what the megaohm reading would be if it was warm, which is kind of nice. But yeah, if you're just using a mega like what you guys have, if you don't want it to be cold and sitting for days on end.
That's the problem, is you'll come to the
But then again, I mean, if it's low, then that's what it's going to be when you hit the start button. So you got to keep that in mind. So it is a real number.
Got a couple questions on the Skype.
Sure.
I want to know how much you charge per hour, and then cost of the tool for like, what do you charge to bring the tool out?
Yeah, so
we've got a rate sheet that varies, but basically, Dave, including the test equipment, is I think it's at 135 an hour. So we don't have an additional equipment rental or anything. So so it's four hours of that. So it's about $500 to have Dave out to test a motor. Though once he's on site, a lot of these, especially if we do like a paper machine outage or something, and we're going from MCC to MCC, and we can test 10, 12 motors in a day, more than that sometimes, depending on the situation. So,
yeah, if they're all in the same room, you could bust out 20 or 30 of them, for instance. Also, then when I get back, I pull the data off of it, put it on my computer, and I look at all the data, and I generate a report for you and send it to you. And we charge $95 an hour for that, so it's a lower rate, but it's still something to keep in mind. And it doesn't take a lot of time, but it's a really important part of doing it.
Oh, absolutely.
And I think that there is an opportunity then for you guys to make a fair amount of money on top of that. I mean, this is a service that I think you could probably sell for $175 or $200 an hour, realistically. So the equipment rental would come into play. We will leave the online test equipment out at a customer site sometimes. So if we're trying to identify a problem that is kind of tough to pinpoint, we have a glass plant customer that we did this with most recently. 200 horsepower motor just shut down sometimes, and there wasn't really any indication of what was going on. It was on an old soft start.
Totally intermittent.
And sometimes it would shut down. And so we tested it. One of our other techs went out and tested it, then Dave went down and tested it. Motor tested good, tested good, tested good. So we said, well, we can leave the dynamic tester on it over the weekend and see what we see. Didn't see anything, and then we brought Michael down, our controls engineer, and he ended up finding a problem over in the PLC. So
we saw that it shut off like 5 times, and they had no idea why. So at that point in time, we knew it must have something to do with the controls, because there's nothing wrong with the motor. But it's neat because I could hook the thing up, and then you could just gap the door, just a little bit of electrical compartment, and I shut it and walk away from it, and it just records until we come back a couple days later, and you can see like all the events that happened, and we could check everything: power factor, voltage, over under voltage, current, harmonics, torque, speed, just about anything you think of. So that's pretty cool too. The online testing is a really good troubleshooting tool. But this is a very strong tool for giving you the condition of the insulation, winding, stuff like that. And it's great for testing the feeder cables too. And we could also test transformers. I don't know if you guys deal with that at all. But was there another question from Skype?
Somebody asked if you could test a motor with that while it's hooked up to a speed drive, to a VFD.
Oh, so no. Just like with your Megger, hopefully you guys are doing this, before you test it, you need to pull the leads off, because you don't want to take a chance of feeding back into the drive and damaging anything. Yeah. So, it doesn't usually, especially the size motors you guys are dealing with, it doesn't take very long to pull the 3 leads off, test it, and then hook it back up when you're done. Is that it?
Yeah, I think so.
Okay. Do these. Okay, so you guys use your digital multimeters, which is good, and you have a Megger, and like I said, the tester we're talking about has all that built into it, and as well as high pot testing. And so what we do, just real quick with that, is we're testing just like what you would do with your Megger. On a 480 volt motor, we're doing a 500 volt megom test, 60 seconds long. And we do the lead-to-lead resistance test, we do the megohm test. If all that looks good, then we start doing these other tests here, the high pot test and a surge test. In the high pot test, we do a test called a step voltage test.
where we go up in increments. So we start at the 500 volt. If that looks good, we'll go to 750. If that looks good, we'll go to 1,000. We go do that all the way up to 2,000 volts because a motor during normal operation starts and stops, and when the contacts close on the contactor, for instance, they're seeing those kind of spikes. And so the motor needs to be able to handle that, but we don't go up that high unless everything's fine. But we're just doing it with microamps of current, so it's totally non-destructive. That question will come up a lot.